Good evening. Very good. So people are dialing in here. I see some more coming in. This is good. So let's go ahead and get started. Human voice. Yes, it's great to hear people. I think we should start with some questions. What questions do we have from the class? So yes, if you check Blackboard for the class Blackboard account, you'll see that assignment 3 had been uploaded and posted there, ready for you to start working on it. I did decide that this will be individual projects and that uh, I've given you plenty of time, got a couple of weeks to do it, but again, you'll spend some time thinking about it, playing around with the tools a little bit, and then when you actually go to write the different input files, it won't take you too long to do that once you understand how this whole thing works. And John's question regarding the mini exam, should we expect the question to be along the same length? Pretty much. It's going to be close to that. It might be just a few lines longer, but in that neighborhood, yes. And it will be pretty quick. I'm not going to give you a whole lot of time to do it. I think you should be able to calculate those addresses and encode the instructions or encode the data in pretty short order, like 10 minutes. Should be able to do that. So for the mini exams, I will be executing the mini exams just like we did the first mini exam, where I'm going to be in the second uh, exam, full exam, where I'm going to build the questions in the tool and you'll have the browser that you can then interact with to be able to read and write the answers. So everything should be good and crisp and clear for you and for us. Other questions? Okay, I guess everybody's excited to get back to the lecture discussion then. So let's do that. I believe we left off here. Okay, so once the macro processing is done, remember we're in the syntactical analysis phase of the compiler, right? Let's probably go back up here real fast. There we go. And change my pointer to that. There we go. So we're down here doing the semantic analysis phase of our compiler. We're reading as input the parse tree or the stack, depending upon whether we're using a bottom up or top down approach, an LL or an LR grammar. And then we're going to do this work that we've been talking about so far, plus the things we haven't talked about yet. And the results of this is that we are going to generate an intermediate code file or a full program listing file. And we can go back and look at that, but you had examples of that back in chapter 2 and 3. Okay, so that's what we're doing here. Is we're going to do all that. Okay, and then we'll also talk a little bit about code optimization at this point too. Okay, there we go. So this is where we left off talking about we talked about the macro processor running, then we talked about the directives that are implemented available in different languages, and this is where we would then do that work. And the result of this is that we may generate additional code depending upon what we've done here, or we've changed values, we'll do substitutions. Basically, that's what most of the directives are about, are doing substitutions or adding code, depending upon what the programmer does in that language. Okay, so once we've done that, then the compiler is then going to go back and look at the symbol table, and it's going to update the symbol table based upon actuals that it evaluated. Everybody can see the symbol table, right? Oh, well, that's not good. It's showing the schedule. Oh, okay. Okay. Okay, it's highlighted in green, so I know that this is good. All right, so what we're talking about, again, as a reminder, we were looking at, so change my pointer back. Come on. Pointer. There we go. All right, so we're in the semantical analysis phase of the compiler, which means that we're reading the parse tree or the stack that was generated in the syntactical phase. And we're going to generate this intermediate code or a program listing file, depending upon what options we were given by the programmer when they were compiling the code. Okay, so that's what we're going to do. Let's go to here where we left off, which was talking about the directives, and we had these examples and walked through those. Okay, now the symbol table is going to be updated as a result of the analysis that the compiler was doing based upon doing the macro expansions and based upon the other work that we were doing. It's going to, in some cases, need to create some new identifiers if it added those, update their values, things like that, or the types rather, and additional entries inside the table as needed as a result of that work. Okay, so in some cases, we did these evaluations of types and values earlier, but a lot of times that work can't be done until we've done this additional work that we just showed and talked about in this phase of the compiler. And as you recall, we were using this symbol table. We created it in the very first phase, and each phase of the compiler is referencing it and updating it up through this time. This is the last time that this table will be updated, but it'll be referenced in subsequent phases. So now we're ready to actually start generating code. So everything's now organized, right, by either items that are queued up in the stack or items that are organized inside of the tree, so that we know the proper order to evaluate all of these different operations and definitions and assignments and those fundamental things that we created and rules for, and then we applied after scanning our input to the resultant tokens, so that they're all now organized in the right order for the compiler to start generating actual machine code. And I kind of foreshadowed this a little bit previous lecture, where I said what we're going to do to help us do that is we're going to use this tool called a quad, which if you're and I know you're familiar with, and everybody has different levels of experiences with functional languages. It's basically what we're looking at with the quads. The quads are organized just like you see here. The very first thing that will be encountered in the quad is the actual operation that's going to be performed. Then the two operands that it's going to perform that operation on, and then where to put the results of that operation. Now, some operations only need one operand. And if that's the case, then you'll only have something in operand one field, and you would leave this one blank, and then you would have where do you put the results. All right, so to help us understand, to see that here, we created this little sequence here where we can take a look at this particular assignment function, which also has two multiply functions, right? So x is going to get y squared times z is basically what we're trying to do here. And we're going to look and see how we could use a quad to actually generate machine instructions to perform that work. To do this, we're going to need some intermediate variables. And in order for us to implement these intermediate variables, we're going to create some sequence where we think there'll be unique IDs. In this case here, we can use something simple like I subscript 1, 2, 3, 4. We'll just serialize them because this is all internal. We're not going to be involving humans with trying to write this code or evaluate it or do any of that type of work on these variables here. So they just need to be simplistic and unique, and something that we can easily create unique instances of every time we need to create a new one. So we'll simply just create a single letter variable name like I or J or anything else, and then just serialize it. All right, so here's how we could then take this equation here, which we would write in code like this, and then to generate machine level instructions, we would do the following. So the first thing that needs to be performed is the order of precedence. Well, we walked through those rules previously. So this is, as you may have noticed, an example of the Pascal language, which says the assignment operator is this colon followed by an equals. And the multiply had a higher precedence than the assignment did. So we would then need to perform these multiplications first. So we'll do this in the left to right. We'll just go ahead and choose a left to right grammar. Okay, so this is lower precedence. This is higher precedence. This one's equal precedence. So we'll do this one first. Now it's really important that you follow that order that I was talking through, because that is what we were showing you in the previous lectures about how to generate rules that will enforce precedence of operations in the correct way. So you need to evaluate them in exactly the same order, depending upon, again, whether you're using a bottom-up or a top-down approach. All right, so the first operation here is the multiply operation, this one here on y and y. So we'll do the multiply on operand 1, which is the first y, and operand 2, which is the second y, but we're not done, right? We're not done yet. So what we need to do is we need to put this result into some intermediate location, and that's where we'll go and grab this first variable. This first variable will be this is the first one, will be I1. So we're going to take this operation on these two operands, do this work on it, put it here. Okay, so we've done this substring. So now we need to take the results of this and multiply it times z. So we have another multiply function, and we'll take the results of this previous operation, which is I1. So that'll be operand 1. And now we need to multiply that to z, and that'll get us, that will calculate this substring here, but we're not done because we'll still need to do that assignment function. So we'll need to create another temporary location to store this temporary result, this temporary value. So we'll do that. with I2. That's the next one in line. Now we are going to do this assignment function. So the function itself is the assignment. So we put the colon equals here. And we're going to take the result of the whole right-hand side, which is this I2, as operand 1. Now this is an example here where we don't have a second operand. So we'll leave that blank. And we want to put the results into X. And so we'll put the X here. And so from here now, it's going to be pretty simple to be, or I shouldn't say simple, because the whole idea is we're trying to write code that can read, go from anybody's, basic, in this case here, Pascal language rules, write some functions that we can then go through and do all of our grammar rules, applying those to set the order of precedence and generate the tokens. And then we can take and scan those tokens and perform translation to the functions, the operands, and where to put those results in a very rigorous manner. We can clearly write code that could say, hey, if we have this quad here, we need to then take and store a variable in a register, take another variable and put it into the accumulator, do the multiply operation on it, and then store it in some location. That's really straightforward, right? So we look up the function and we know what the function is going to operate on, like in the assignment case. And for an assignment function, there aren't two operands. We only know there should be one operand. So we'll take that operand and we're going to store it in some memory location specified here. So however we generate the address for this, that's the other work that would have to be done. And when you read through the textbook, it actually has some code examples of how to go from the quad, and just like we talked about here, generate the machine instructions to generate these actual machine instructions for these different functions. So you should be reading through that, pick a couple examples and read through that and walk through it, make sure that you understand this. I will be expecting you to be able to take expressions with specific functions in them and be able to generate quads for them. I would be able to expect you to do that, yes. So any questions on quads? So there was one up here about, is I representative of a byte in memory? And not necessarily. It could be if we're saying that every variable is going to be a 3-byte, sticking with the SIC and XE family of machines, if every variable is going to be by default 3 bytes, then I would be the address of the first byte of that 3-byte word, yes. So Ron asked if these quads are generated directly from the stack and tree, and the answer to that is, I'll say yes, but remember we've done some additional work as we've been popping these off the stack, or pulling them off the tree. What we're doing is that other work with the macro expansions and such as well. So all of that code is laid out before we start generating quads. We've got all of the code fully expanded. All of the directives have been evaluated and additional lines have been populated as a result of that. So now all those tokens, because when it does that, when the macro expansion happens, it's also going to have to insert those nodes into this proper place in the stack and the trees as well. So yes, it's going to then take those tokens one at a time off the stack or tree, because that is the order in which the program needs to run. Other questions? Okay, so let's take a look at another example then. Okay, so in this case here, we have the variable or symbol variance. We're going to set it to the value of sum square with the division operation with 100. And we're going to subtract mean times mean from that. Okay, so we'll go ahead and start where we were talking about, it's already, we already have the tokens built, right? They're already organized inside the tree, and we're going to pull them off that way. So when we did that, we saw the highest level precedence, of course, in this whole thing. If you're just looking at this flatly, just going from left to right, you can see that a div and a multiply and a minus and an assignment are the four functions that are in this one statement here. And of those, the divide and the multiply are the highest level precedence, and they're equal in precedence, which mean we'll do the left to right evaluation. Then it would be the subtraction, and then it would be the assignment. So that's the order that they've been put into the stack or the cube. Okay, so that's what we're going to do is we're going to say, this first divide is the highest level precedence, and its two operands are sum square and 100. So the first quad that we would then generate will be the div function, followed by operand 1 sum square, followed by 100. It's immediate value, so we indicate immediate value here as 100, and it's only a sub part of this whole expression, so we need to create a temporary variable to store that result into. So we'll do I1. Okay, then the next thing that would be off the tree would be this multiply operation here. And the two operands are mean and mean. So we'll do the multiply function, operand 1, the first mean, operand 2 is that second mean. And again, this is a substring of this entire statement. So we need to put that into a temporary location. So we'll get another temporary variable, I2, and we'll put the results of this multiply function into I2. The next level of precedence of what's remaining would be the subtraction. So we'll do the subtraction function. And now we have two operands, the left side, which is I1, and the operand 2, which is the right side, which is I2. So we'll do minus I1, I2, and we're not done yet because we're still here. We haven't evaluated this function. So we'll need to create another temporary location, I3, and we'll put the result of that subtraction there. Now we can come and do this assignment function. We have all of this evaluated, and so that's now an I3. So we'll do assign I3 to variance. All right, and now to show you how you could generate code from this example here, okay, what we need to do is put sum square into the accumulator register. So we'll do the LDA sum square. Now we have that in the accumulator. And we have an immediate value here, so we can just do a divide with that immediate value. And then we can do the store accumulator register into a temporary location here. Now we could have used I1. We decided to show you that we can use other variable names. So we'll do T1, and just to show you, you can. Okay, so we'll put that into temporary 1. Okay, now remember that value is still in the accumulator register. However, this next function here is this multiply function, and we have two operands. So we need to take one operand. So we'll take that first operand and put it into the accumulator register. So we'll do the load A, the load accumulator register instruction with that first operand, mean. And now we can do a multiply with the symbol mean. We have it right there. Again, we need to store that temporary value. So we need to do a store A function of T2, or that value that's in the accumulator register into location T2. Okay, so the next thing we need to do is the subtraction. We need to subtract I2 from I1. So what we're going to do is we're going to do a load accumulator with T1. That's what we're going to do the subtraction from. Operand 1 is T1. Okay, so we put that into accumulator register just like we do in all of these. We're organizing these so that the first operand is what will get loaded into the accumulator register. Now we could do the subtraction of T2, the temporary variable 2, which is the I2 here. We do that subtraction here. And now this is combining a little bit of optimization because technically we have this here which says we should be doing a store accumulator register into T3. However, it is okay for the compiler to do a look ahead one and say, oh, the next function is a store accumulator function, and we already have this in the accumulator register, so there's no need to do a store and then a load. It's already in there. So, and it can actually temporarily generate the code and then see that, store A to T3, load A from T3 can be optimized out, and then it can do it that way. That's the safest way to do it because it's a little bit more work, but it ensures that you absolutely have the same value inside the accumulator register when you do this optimization. So we will do that at this point. And we can then generate the store A to variance. And that's how you would get to evaluating this to generating machine instructions. So, okay, thank you. This is a good slide. I like this one. That's good feedback. I'm glad that works for you as well. And yes, you should be expected to be given questions like this and be able to do this analysis and generate the quads, and from quads be able to generate some machine instructions for from some fairly straightforward things. I'm not going to give you anything too complex on an exam. So looking at John's question here, the second part of it, could we have the quad set to be I2 instead of I3? No. No, we want to generate, when we're generating the quads, we want them to all be unique because we're doing them one at a time with no look ahead or look behind either. Because we talked about look ahead, but then during for this optimization down here, but then I backtracked and pointed out that it's a lot safer for us to look at if we did a store A function, look at the location here when we're looking at this location in the next function to see if we have a store followed by a load. Because if we have a store followed by a load and the memory location is the same thing, T3 or I3, then you can get rid of those two lines of code as an optimization function, because that's the only way you would know for sure that you have the right value already in the accumulator register. And yeah, that's the only way. Now, it doesn't have to necessarily be an assignment function. It could also have been a subtract, any of these functions really. It's what we're really saying is that if operand 1 is the same value as your location on the previous, it's probably already in the accumulator register. Check and see. We did do the LDAs and the store A's, the load A's and the store A's here, and we did them here because these were different values, T1 and mean, T2, T1. If we had included the store A and the load A here, it would have been T3 and T3. So if we have a load followed by a store and these two values are the same, then we can optimize that right out. Likewise with the subtraction. If we did a load A and subtract itself from itself, well, that's different, right? Because now you got this is the second operand field. So that's not quite the same thing. So you have to make sure that when you're doing the loads and the stores, you're talking about a sequence like this where you have a store followed by a load, store accumulator followed by a load accumulator. It could also be a store B followed by a load B, right? Base register, or an L register, or a T register. So whatever register you're doing pairwise operations on, if you're doing a store followed by a load here, and if you're doing the same thing with this, because that's the only place you would do that, then you can optimize that out. Yeah, Dante, that's a pretty safe bet. Yep. As well as, like I said, generating quads. I would think there's a high likelihood of that being on the exam too. Okay, makes sense for the questions. Okay, moving ahead. Yes, generating this quad from this. Generating a quad from this. Or other expressions. Any expression is open game. I'll probably leave it, I don't know. Will I leave it to just expressions or will I include some other constructs? I'll think about that and it'll be in the study guide, which I'll post soon. Okay. So that was it. When we finished this part here, we've generated the code. What we didn't talk about was calculating the addresses. But that's the other part that this phase of the compiler is also doing, because it's going to be generating that listing file that we talked about, which means it's going to also need addresses. Everything will be generating machine instructions with the proper variables. It'll be calculating the addresses, which we talked about before. And the reading in the text has actual code there that would then could be executed to do that work. So it's worth reading through there to make sure you understand how to do that. So yes, we're going to generate, it's going to do this stuff. We talked about generating addresses before, so I didn't think we need to revisit that, but that would also be done at this phase of the compiler after it's done this, where it's actually generated the machine instructions using the variable names, including the temporary variables, and then calculating addresses so it can actually encode each machine instruction or encode the numerical representation for immediate values and so on in order for it to actually generate code that will execute correctly in the machine. So the next phase of the compiler then is about optimization. And we're not going to go into too much detail on this. I'm not going to necessarily test you on this other than maybe talk about some, well, I'll work it out and then I'll put that in the study guide about what I want you to know about optimizations. But what you need to know is that in the optimization phase, what we're looking for are things that once we've done all this, once we've done all the work of generating the tokens and organizing them into either a stack or a tree, and then generating the quads from there, a lot of times the code is now reordered in a different way so it'll run correctly, but it looks different than it does to the human programmer working with that language. And so one of the things that pops out at that point are things where we may have actually included duplicate statements. We may be doing the same thing twice and we don't realize it when we're writing code at a human readable source code level that it's really a duplicate function. We already did that work once. And a duplicate function could be something like, we did some arithmetic expression and we put the results into the T register. And then later on, we we maybe retrieve a memory location, which is where we may have stored that value, and put it back into the T register. Well, there's no need to do that twice. So we'll be able to quickly and easily find those. When I say we, the machine actually executing the optimization code after all the assembly code has actually been generated, will be able to easily identify where those duplicate statements exist, and it'll remove one of them, usually the second one or the third one. If it's multiple, keep the first one. Likewise with sub-expressions. And by sub-expressions, I mean things like this could be a sub-expression. And we might use it once here, but 40 lines of code later, we do that work again. Well, as you can see here, sum squared divided by 100 is stored in this temporary location I1. So where we use this sub-expression later on, we don't need to do this work later on. All we have to do is go grab I1 instead. When I say we, the compiler in the optimization phase would encounter this a second or a third or a fifth time. They'll say, instead of generating this actual machine code here, let's just go and use I1 where you were going to use this the next time. And that way you could skip that work. Yes, that is why we need to keep them there, so we can use that work for optimization. When we finish compiling the code, if we don't need to use those temporary variables again, then we can delete them. If we only use them just the once, use it once and delete it. We can do that. But we can't do that until we've gone from the very first function to the very last function in the code that was put into the stack or the queue, or the tree rather. Okay. So that's the common sub-expressions. Constant operations within loops, same type of thing. We identify those constants and we go ahead and set it to whatever register we're using it, or do that, or maybe if we can reorder the evaluation of the expressions so that we can save ourselves from having to do a store and a read again and still get the correct answer, then the compiler can do that during the optimization phase. Okay, we talked about store and load. And also in the reordering of our code, we look at our register usage and we look to see if we can change simply by changing the order and still being able to evaluate correctly, if we can optimize the use, minimize the use of extra registers and things like that, or if we're doing a register to register operation. If that makes sense, we'll keep it. If not, then we can just bring an immediate value in a single register operation, things like that. Likewise with array usages, we're going to look to see, again, an ordering sequence, if there's a way that we can order it based upon how we're using the arrays, how we're actually going through the arrays, like if we're just going and cherry picking a few values, or if we're going to go sequentially through it, if we're going to go through it in column order, or if we're going to go through it in row order. We'll take a look at how we organize the arrays. And that's a big one right there. If the operations that we're going to use on these array functions are cherry picking, then it really doesn't matter too much. But if we are reading through a whole record or most of a record before advancing to the next record, then we want to be in row major order and organize our data structures that way. But if we're always looking at field 3 or column 3 of our tables, then we might want to reorganize the table to be column major order so that we could then optimize the runtime performance so that it could more quickly go through that matrix or that data structure and be able to get the values using some optimized register operations instead of recalculating addresses every single time. So there's a lot of things like that that can be done and typically are done in the optimization phase of the compilers. And as you can see, they're pretty straightforward. Once you break it down to the low level component that we are in right now, it's to build these. So the optimization, yeah, I should be clear about that. The optimization we're talking about here is specifically for the runtime, to improve the runtime performance. It's obviously going to take more compile time to do these different optimization techniques. So when we run these, it's typically for the idea that we're compiling a program that's going to run many times, so it needs to be optimized for runtime performance, which is one of the reasons, which is the big reason actually, why optimization flags are options that you feed to the compiler at compile time. So by default, it's going to do some optimization, but it's not going to do a lot of optimization, because you might want to be working on developing the code, and you don't want the compiler to spend all that extra time doing optimization after optimization when you're just running the program once or twice, generating some error conditions, going back, debugging your code, and recompiling it again to see if you can get further along. So in that case, it doesn't really help you at all. Actually, it will slow you down to run compile time options while you're debugging your code, until you get to the point you're debugging that you're looking for performance. In that case, yes, you want to include those switches, those options in your compiler's input to do the code optimization, so that you can have a better representation of your runtime code to do your runtime analysis with. Okay, then we generate the code, translate the actual machine instructions, the addresses, generate the executable file, the object files, and then the executable file that is. So we do all that work. One of the things that we're going to do when we're calculating these addresses is that we are going to calculate the addresses of things like our arrays, or the structures, unions, complex variables, things like that. We are going to need to generate addresses to get to every row, column, position inside of that structure. And so when we create some more complex structures and unions, which have combinations of, char arrays of various lengths and integers and floats and stuff like that for one particular location, we have to still get to each of those individual items inside of that one location. So we're going to have to determine those addresses, or build an algorithm that can generate those addresses, so that we can calculate those addresses during this phase of the compiler, so we can get to those specific memory locations to get to that specific field in that specific data item in that specific data structure. So since some of these things we saw the compiler can do, like when we're doing reserved words, reserved bytes, and even bytes and words, the compiler can calculate those addresses for us. But now we're talking about data structures that we as programmers are defining, and for the compiler to generate addresses for those is going to take some more work in order for it to do that, because this is a dynamic thing. Whereas you might think of reserved byte and reserved word as dynamic, but it's not really, because it's fixed. You say reserved byte and you give it a number, and that's how many bytes that compiler is going to generate it. So it gets a value and it's got a function. It knows to skip over that many bytes, and the next instruction following that reserved byte, that gets that next byte address. So those are pretty static, even though they're taking a number as an input value. They're still statically defined. But in this case here, the addresses for these are not statically defined. We're going to define those dynamically as we are writing the source code. And so for that, the compiler is going to have to generate a way to navigate through these more complex data structures. And we're going to take a look at that. Okay, linker, link editor loader, we talked about those in previous slides. So let's talk about these addressing functions. How are we doing here? Oh yeah, perfect. Okay, so in this example here, we're going to build a matrix. Okay, and this matrix is going to look like this. Now, for those of you who aren't familiar with this syntax, this is how you would define a matrix using an Ada program. So this is like Ada source code. And the way you would read this is we're going to create an array. We're going to create a type array. We're going to name it A. The array is going to have two different organizational structures to it. So our axis in this case. So in this case here, we're going to specify rows, and here we'll have columns. And we're going to say that this array is of type integer. And we're doing this for the SICK-XE machine, which means that we know we're going to be working with 3-byte words. All right? So let's see if we understand a couple of other things we put in here too that you might not be familiar with. In the case of Ada, you actually get to specify what the lower value and the upper value of the indexing fields are. So in this case, to keep it kind of straightforward, we're going to say, okay, for the rows, we're going to go from 0 to 3. And for the columns, we're also going to go 0 to 3. It's pretty straightforward. We have a 4x4 square matrix. Pretty straightforward. We could, but the thing is, we could set this and this to other values. So if we wanted to go from -3 to 0, we could have done that. If we wanted to go from 1 to 4, we could have done that. And then these values could be different than these values. And if you're not familiar with languages that allow you to do that, you're scratching yourself saying, why do you want to make yourself life more complicated that way? And the answer is the reason why we're creating source code level code for humans to work with is we're trying to come up with higher levels of abstraction of the machine that we could then write instructions for that could be interpreted by the compiler to generate actual machine instructions to do exactly what we want it to do. Now, we're also, as you've seen in other assignments, where we are taking the requirements and we're also distilling them down to detailed requirements that we could then generate source code for to do the work that is needed to meet that requirement. And we're trying to do this so that we can generate as few errors as humans as possible and be able to generate from humans what we can write to machine instructions with as few errors as possible. So when we do things like construct an array and we're doing it for numerical purposes, then we probably just want to use numerical values. However, if we are building an array because what we want to do is control something like a flight surface on an aircraft, then we probably don't want to work with numbers because we as humans would then have to translate a range of numbers that a flight surface on an aircraft could go into something that will generate the correct values for those servos. What am I talking about here? So here's where a whiteboard would have been handy. But if you can think of, for example, the rudder, right? The rudder on an airplane. Let me do this. I can draw, just not too well. So let me see if I can do this. I'm sure I can. Okay, so we have the airplane. Oh, that's big. Let's get a smaller one. Okay. There we go. So we have an airplane. And back here is the tail, and the rudder is this thing here that goes left and right. Okay, so it has a range of values that we can swing this rudder to port and to starboard too. So let's say that this aircraft is designed such that we can have maximum rudder 18 degrees to port and 18 degrees to starboard. Okay, so we can designate, for example, 0 to -18 or 0 to +18 using this kind of nomenclature here, in which case that would be pretty simple and straightforward, and we don't have to really worry about translation too much. What really gets challenging though are things like the wing flaps, because in the wing flaps, and that's these pieces here, and there's also the rear wings. The wing flaps, the wings themselves are already canted at a negative position. And then what the pilots can do is they can order it from one negative value to another negative value to let the flaps down, or we can let it pass 0 and go a positive value to go up. So if the aircraft were designed such that they can go a maximum of 39 down, then we would start with -39 to 0, or -39 to, let's say the maximum was going to be 18 degrees up, then we might have -39 to 18 would be the range of values that we would use here for this element. And that way, we're not having to write somewhere what the equivalent values for 0 to 42 are. We would simply have the actual values inside the code here, reducing the likelihood of errors being introduced by the persons writing the code, by the persons testing the code, by the persons doing QA, quality assurance on the code, people who are doing modification to the code. Later on, it needs to be upgraded because the new version of the wing allows 2 more degrees of movement, and so they got to change the values here. If you have the actual values here, you are reducing the likelihood of error in every one of those steps. So that is why languages like this are important. And that's why we might want to choose a language like this for doing some solutions, because that way we can reduce the likelihood of errors by avoiding rather sending programmers and testers and QA people and people updating code and stuff like that to some table somewhere, doing the addition subtraction themselves and coming up with the new values, and hopefully they got them correct, or they wrote them down correctly and they couldn't read their own writing and put a different value in the actual code. Lots of different things can happen. So that's why we have languages that allow us to do that. But having that means that we're adding more complexity to how we're going to generate these addresses. So that's why we are going to figure out how to calculate these addresses using this example with something like this. Let me change my pointer back. There we go. Let's see what's in the chat window. So John had a question here or a comment. Accessing a matrix, we use any of the 3 bytes relative to the matrix number, must be the beginning byte. We're always going to start with the beginning address of this particular structure. In this case, this is an array, yes. Okay, so let's talk about what this all means first, and then we'll go through an example. So what I did is I took this 4x4 matrix and I calculated the 4 rows, and then each row has 4 columns. So we have row 0, column 1, column 2, column 3, row 1, column 0, column 1, column 2, column 3, row 2, column 0, column 1, column 2, column 3, and row 3, column 0, column 1, column 2, column 3. Now each one of these is a word wide, so each one of these is 3 bytes. So 00 is byte 012. 01 is bytes 3, 4, 5. This 02 is 6, 7, 8, and so on. So what we have now is the starting byte of the first entry into this 4x4 matrix will start at byte 0 in this example, and everyone's 3 bytes long. Now, knowing our organization is like this, we can also say, oh, we know that the first byte of row 1, which is the second row, is going to be the 12th byte, or the byte number 12 rather, which is the 13th byte. Row 2, 24, row 3, 36. We know that because we knew that the length was going to be 3 bytes times 4 elements, which is where we got the 12. So we have that. So now we can get to, we have a value for the starting byte for every element in this 4x4 matrix. But how do we do this numerically? How do we write an algorithm to do this? That's the question. So we start by looking at the specification, where in this case, the specification is an array type, a type array named A of type integer, where the lower value is specified, the upper value is specified of the rows, and the lower value is specified and the upper value is specified of the columns. Okay, so what we have to do is we're going to create some variables. Let's come here first. L is lower address, U is going to be upper address. And then W, we need to let be word size. And that's the reason why we have integer here, is that way we know, an integer is going to be a whole word, so that's 3 bytes. So we'll have to set W to word size, which in the case of the SICK-XME machine for an integer is 3. Then we have rules about how we access this theoretical array here. To access it, then A is going to call A at some address, and the address are these index values, and we'll use S1 and S2 as the 2 calling values for 1 and 2. Now, given that, we can generate an algorithm to calculate any relative address relative to the starting byte of this particular array. So that calculation would be word size, and I probably should move it over here at the end so we don't get all hung up on that, but we're going to take word size and multiply all of this by however many bytes we're jumping over. And what we're talking about in each of these terms is we're trying to figure out how many bytes do we need to jump over to get to the next row or column or element. So let's look and see what we're doing here. First thing we're doing is we're taking S1. Well, that's the location we want to get to. And we're going to subtract L1 from that. So if it was 0, then we're not going to be subtracting anything, right? It's just going to be whatever it is minus 0 is unchanged. But this is the case where if we did allow a language that specified some value other than start with 0, so you don't have lower and upper, you just have a single value, for example, like you're used to in C and C++ and Java and a bunch of others, then you don't need to do that. But for a language like this, you would need to do that normalization. And we could do that here without error, simply by taking and subtracting what that lower range value is for the rows from S1 when we're calling that array. So we're going to take that and we're going to take whatever row we want to jump into, and we're going to multiply the rest of this times that. So what we're saying here is that this term is going to jump over rows. So if this was 0, if we said S1 was 2 and S2 was 0, then we have nothing here. All this would come to 0. So we would just have S1. And if it was 2, we wanted to go to row 2, then we would simply need to say, we need to figure out how to get word size, which is here, 3 times that. And maybe there's a little bit more work that needs to go on in here, because how did we get to 24 from there? All right, so we still have to worry about these terms, even when it's 0. So let's go ahead and finish this thought. Okay, so we're going to take this row jumper term and we're going to multiply it times this. Well, what's this? The first thing we're going to do is we're now going to take and look at the difference between U2 and L2. U2 and L2. what is the range of those values, and we're going to add 1 to it. This gets us to normalize to the 1 value, okay? And now we take it, add that to normalize S2 minus the starting location of L2. That will then do that correction when this is 0. So if we called in 0 here, and this was a 0, then that's a 0, but we still get that 1 here. So we'll have 2 plus 1 is 3 times 3 is 9. That would get us there. Okay, now let's take a look at this example here. Let's say we created this array. We defined it this way, 0, 3, 0, 3, just like we've been talking about. And now let's take a look at these values, L and U. Okay, so W is 3, L1, U1 is 0 and 3, L2, U2 is 0 and 3, just right out of there. So now we have those variables defined. So now if we want to call this array A, and we want to go to column 2, word 1, we're simply going to plug in these as S1 and S2, right? That's S1 and S2 here, and plug them into here. We now have numbers for each of these. So here we have S1, right? S1 comes down here. That's the 2. Minus L1. L1 we said was 0, so 2 minus 0. We have 2. Then we come here. U2 minus L2. U2 was 3 minus L2, which is 0. 3 minus 0, so that's 3. But we've got to add that 1 to it so we can get to that next term. That'll give us a 4. So now we need to add how many columns do we need to skip over? That's where this S2 comes into. We've got to the right row. We're now at the right row, but how many columns? So we'll take columns, which is S2, 1, right? Minus L2, 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 L2 was this term here is 0, right? So we have 1 minus 0. So we have 1 here. We have 4 here. We have 2 here. 1 here, 4 here, 2 here. And we're multiplying all of that times 3, which is the size of each of these cells. So that's where we get 6, 7 times 3. Yeah, 2, sorry, not 6, 7. 2 times 4 is 8, plus 1 is 9, times 3, there we go, 9 times 3 is 27, which calculates this byte here, which is the first byte of row 2, column 1, which was what we were trying to get to. So if we want to create a 2-dimensional array of any size, we can do that. We can use this algorithm here to generate the correct addresses for each entry in that matrix. 2 by 8, 14 by 65, whatever. Type integer, type real, type char. You can do that too, right? Char is just 1 byte. So you have here the actual algorithm to be able to calculate the correct address of any element within that structure, given whatever type it is, and it will by evaluation be able to generate the correct address when you call a specific element entry in that array. And then you can extrapolate on this to use this algorithm, or to extrapolate and build a similar algorithm for other types of data structures. Once you understand this, where we're just trying to jump over rows, then get to a specific column within a row, and then set the width of each element, you can calculate it. And then for actual runtime addresses, we already seen how you could take a relative value and make an absolute location from it if we need to. And when we go in to load it, we can just update that first address at that point and then make everything relative addressing after that, and we're good. Any questions? By the way, this is another fun one that shows up on exams sometimes too, is something similar to this, where you might take an algorithm and either generate an algorithm like this or modify an algorithm to generate addresses for other types of data structures. Those are fun things to do. All right, any other questions? All right, back to the mini exam. So for Monday, what we're going to do is we will have lecture. And at the end of lecture, I will then enable mini exam 2 and give you 24 hours to complete it. But it'll be timed. So you'll only have 10 minutes, I think is what I'm setting it to complete the work once you start it. So I'm estimating next lecture to take about 30 minutes. So most likely we'll start at 5:30, of course. Most likely we'll be starting the exam at 6 or 6:15, something like that. But again, you'll have up to 24 hours to start and 10 minutes to complete. Other questions? No problem, Dante. 10 minutes. There you go. John's got it. And Austin's asking about the exam. So some of those exams didn't scan too cleanly, but I can do better. I can do better. Okay, so essentially what I was doing was I was asking you in question number 6 on the exam, I gave you some code and I solved some addresses and I encoded some instructions. And then I left the others blank for you to generate addresses and assemble instructions. And so that's what we'll be asking you to do on the mini exam. Okay, great. That is helpful. Some people are concerned about finishing that in 10 minutes. 15 at the most. And I get it. You're calculating things, but you still have to enter it. So yeah, I can give you a little more time. Sure. 15 it is. Sold. Nice, Ethan. Nice try. No. Other questions? Okay, well, I hope everybody has a nice and safe weekend and stay healthy. Be working on your readings and working on preparing for the exam, and wish you all the best. And we will see you on Monday.